Okay, good afternoon, everyone, and welcome to this seminar. And it's my pleasure to introduce Alberta Longhini, who is going to present her work towards general manipulation of deformables. And she's a PhD student at KTH, supervised by Danica Kragic. Please, Alberta, take it away.
Hi everyone, thank you for being here and investing some of your Friday time listening to this presentation. As Peter already introduced, I'm gonna talk about towards general manipulation of deformables. And specifically with deformables today, we will talk about the category of clothes, 2D deformable objects and garments, for example. And the reason why this is a relevant topic is because textiles and garments are ubiquitous in every part of our life. Either is dressing ourselves, doing laundry, or cleaning your house. This category of object is present and requires specific manipulation strategies due to their deformable nature. And while we do see some form of automation in manipulating this category of objects, the solution that we do currently see struggle to be applied to different objects. For example, what we do see here are successful manipulations of these objects, but if you remove or change the type of object, for example, the t-shirt with a sweater or a skirt, most likely these solutions are going to fail. So what we would like to discuss today is how can we adapt manipulation of these deformable objects to different variations of these objects towards general manipulation skills of robots. And this is particularly challenging because deformables introduce some challenges that are not common, for example, when manipulating rigid objects. Especially, for example, self-occlusions. If you deform the object might occlude some parts and make them not visible anymore. But especially one of the biggest challenges, especially in these days where data-driven and machine learning models are popular, is the lack of data. This category of object is often underrepresented, making hard to learn policies that generalize to different variations of objects. But before moving on, let's try to understand first what manipulation of textile is and what are the different components. The main component is the robot interacting with the real world, with the environment. And while there are different ways for robot to decide what's the best action, the focus of my PhD was on model-based techniques. So techniques that relies on having a model of the world, or in this case, a model of the object or of the garment, in order to make informed decision making. Which doesn't mean that model-based techniques are the best across all the possible techniques, but there are some benefits that if you're interested, I can expand later on. But this is the category of the class of methods used in my thesis. And once we have a way for the robot to interact with the real world, then it's important that the robot perceives the feedback provided by the world, so the world can manifest through image observations or depth observations. So the robot must possess the capability to perceive, for example, what type of objects or what are the properties of the objects in order to adapt to the variations of these textiles. And this is an important module. Perception is fundamental because the robot needs to have an understanding of the world that surrounds it. And along with this perception is finding a suitable representation. So the robot needs to have a way to represent the world is operating with it. And I think that once we have this representation, that we are not done, because one of the most important thing is to feed back this information that the robot processed and then perform other decision making based on this feedback. And this creates the manipulation loop. So the action perception loop, that if closed, it means that the robot is capable to interact with the environment, observe from the feedback that the environment gives, and then use this information that is fed back to the robot to adapt if something changes about the environment, or to correct mistakes, as what the robot performs might not be always the best. And this is basically the manipulation of textiles, so the framework we want to work on in order to adapt to object variation. So the rest of the presentation, I will give a fundamental about textiles or garments, so we are all on the same page of what we are discussing about. Then I will discuss some challenges in achieving adaptation towards this overall overarching goal, that is generalizing manipulation of these class of objects, and some of the advances introduced in my work, to finally conclude with a couple of emerging opportunities that my work, but also current advances in the field, present. So what are textiles? I've been using this term, but I think it's important to understand this class of object, especially because we are talking about adapting to variation. So what do we really mean with variation? So textiles are a class of object that starts from raw fiber that are spun together to form yarns, and then these yarns are knit or woven together to perform fabric. And fabrics are the first category of object that can be classified as textiles. Then these fabrics can go through different production processes like cutting and sewing to form clothes, but not just clothes. You can think of blankets or bandages using in healthcare settings. All these objects fall under the category of textiles. So if sometime I use fabric or garment or cloth interchangeably, you need to be aware that there are subtle differences, but overall they all fall under the category of textiles. And these are the type of objects that we are discussing today. And the reason why I started with this slide to talk about textiles or cloths is because this production process is what defines the variations we're interested in. For example, starting with cloths, we might have a skirt or a blanket. This is already one type of variation. But for manipulation, another type of variation that we're interested in are its mechanical properties. For example, what you are seeing in these slides are two cloths with different elastic properties that are pulled with the same force. So the robot is applying the same force to this object, and you can clearly see that the deformation this object undergo is quite different. And you would like the robot to be aware about this difference, because, for example, if the robot is tasked to dress someone, then it's very important for the robot to be aware whether the garment is dressing is elastic or not, and design or operate with the care that is needed in order not to harm someone, which is different whether the object is elastic or not. But elasticity is just an example. In this case, you see the robot performing the same manipulation, but because these two objects have different shape, or not really shapes, but sizes in this case, different thicknesses, then the outcome of the same manipulation is different. And this is why we're interested in adapting to these variations, because we would like the robot to be capable to perform accurately, independently on these variations. So I hope that at this point I convinced you that there is some need of taking care of these variations among objects. And we can move on to discuss why it's hard, why the previous methods or current solutions struggle to consider these variations, and how my work addressed some of these challenges. So let's start for now to the first part. So let's assume that the robot interacts with the environment, with the object, and the object provides some feedback. Then the question that we do have, how can the robot perceive the properties of the object? Because that's the first thing that we want to understand, so perceive these different variations. And this is hard because we do not have labels. What does it mean not having labels? So I guess that most of you have done laundry at least once in your life, and there are these cloth tags providing you material properties. So you know if it's made by wool or polyester, so you can plan accordingly how to wash. But this does not really inform you how elastic it is. There is some correlation, sure, but you don't really know how elastic the object is, how stiff. And the reason is that it's not that easy to extract these measurements. While there exist some tools in the textile industry, most of these tools are destructive. And we don't really want to cut a piece of cloth just for sake of understanding how elastic it is, which turns in lack of labels to study this problem. And a way to tackle this issue is to use the concept of intuitive physics. Intuitive physics is the human capability of gain an understanding of how the physical world works just by interactions, without having a precise knowledge of the physics or the real physics, but just by observing how the world behaves, how interaction outcomes are, and form this sort of intuitive understanding of the physics without precise labels. And the way this translates to robotics is basically, let's assume that we have a robot that has to manipulate this object. What the robot has is an internal representation of this object, where in this case the object is represented as a mesh, and the robot in his mind think of some actions and what the outcome of this action could be under the assumption, for example, that the cloth is flexible. But when the robot performs in the real world this interaction, you might observe that the outcome does not really reflect what it thought at the beginning. And maybe thinking that the cloth might be stiffer might better represent the current interaction. And by performing this sort of interaction with multiple objects, then the robot can start understanding what's a stiff cloth, what's a less stiff cloth, and improve his internal model of the world. And in one of our work, actually, we show that this works. So if you provide the robot with some pulling interactions like the ones we saw before, and we have a perception model that extract some physical properties, that the way you need to think about these properties is not the precise value of how elastic the object is, but some sort of understanding of what elastic means, such that combined with a dynamic model, the robot is then capable to make accurate prediction depending on the outcome of the interaction. If you substitute this red cloth that was very elastic with the gray cloth that was more rigid, then the dynamic model will adapt accordingly. And in a follow-up work, what we showed is that this indeed enables to adapt manipulation of textiles and cloths. For example, these two cloths have very different elastic and stiffness properties, and the robot is capable, by observing how the object behaves, to adapt the manipulation accordingly. And this works also for thicker cloth, like for example these folded pants, but also for different shapes, like in this case folding the leg. Which is more or less what we wanted to achieve in this case. We wanted to have a framework to manipulate objects that was capable to adapt. So in case of variation of shapes or mechanical properties, the robot is capable to observe the world and adapt accordingly. But to be really general and autonomous, there is one big problem here, which is the assumption that the robot knows how to handle these variations. While in the real world, there might be scenarios where the robot encounters objects that is never seen. So his internal model is inaccurate. So this is why what we want to do is to make sure that we have a way of representing the world such that when we have feedback from the environment, we can leverage this feedback, for example, to detect mistakes that we made and especially to correct our mistakes. But this is very hard because, in particular, here the representation is very important. What type of representation is suitable for endowing robots with capability to detect and correct their errors? So here you see some common representation of textiles, going from images, point cloud, particle, and meshes. The most common representation used in analytica simulators, so based on physics, are particle and meshes. But the reality is that the real world most of the time provides us with images and point cloud as feedback. So in some way, we need to find a way to connect these structure representation, for example, meshes, as we used them before, with what the world gives us, that are images and point cloud. And this is a very complex problem. And let me show you why. So here we have two different configurations of clouds. One is a completely flattened configuration with its point cloud. I think that here is clear. We can clearly see all the points. But in a further configuration where the cloud occludes some parts of it of itself, and we observe a point cloud, it's not really that easy to understand all the parts of the cloth. For example, you can see that this is the upper layer of the folded configuration, but it's not trivial to extract them. Which means that if we wanted to obtain, for example, a mesh representation from the real world to observe whether our model predicted the correct state, how can we do that if, for example, what we observe are only images and point cloud? So the last question that we want to discuss briefly now is how can robot can detect and correct errors in model prediction, given these challenges of representing cloth and observing the state representation from the real world? So the assumption is that like we have a model of the cloth and a 3D state, and our robot is capable to predict future states, but the only thing that we do observe are images. And while detecting error, for example, it can be done by, for example, projecting the 3D prediction over the image, and you can see that the overall shape covered by the 3D state does not match the image one. What we can still see that the problem is lack of labels. We don't have labels in the real world about the ground truth 3D states, which as again, now we need to find a way to address the problem. And the tool that we use to address this problem is Gaussian splatting, which is a computer vision technique that what does is to create a bridge between 3D state and RGB observation. I won't go into details of Gaussian splatting, but we can discuss it further later if you have some questions. But the main thing of these tools that I would like you to take with you is this bridge. Because if now that we have a way to connect 3D state with RGB observations, what we can do is take our 3D state that was wrong at the beginning and our image observation and correct it just by using image observation, thanks to this bridge that Gaussian splatting created. And the outcome is that now we have detected that we had mistakes and then we corrected it. We corrected our 3D representation even if we had only image observation. And as a result, for example, is that you can track these 3D states only from image observation. And here you can see that the occlusion caused by the cloth on this lower part of the cloth are high. Nonetheless, we are capable to still collect this information from RGB observations. This is a way for a robot, for example, to interact with the object, assume or make some predictions, thinking of what could possibly be the future state, apply the action, and correct based on the feedback from the environment. Which leads to the end to the closure of this action perception loop, where we perform some actions, we used perception to infer properties and variations of this object, but we also found some suitable representations such that the robot can use to detect and correct errors. Which in the end leads to what we wanted, a way to adapt to object variations. So what can be done with this? So what are the future direction that I envision for this line of work? So one is lifelong learning. Where with lifelong learning, I intend the capability of robots to keep interacting with the environment and learn from the environment. So the capability to, first of all, learn about the physics of the environment by interaction, but also to correct possible wrong intuition and models that the robot has. And this doesn't have to be just for the class of deformable objects I discussed, because deformables are wider than just textiles. You can include also 3D soft deformable objects like sponges or plashes, but also for rigid objects. This is still an open problem, and I think that is a very exciting and ultimately what we would like to have. Well, the second thing is better world model. I think that some of you must have seen recent advances in generative models in generating these very fancy and nice um, clip of real world, but the physics of this model is not that accurate. And I think that one of the reasons is that learning physics is very hard, but the truth is that we also have a knowledge of analytical models that has been developed previously to these data-driven techniques. But the challenge is that these models are often in the 3D dimensional space, but this image generation that we have is in the 2D space. But there exists a bridge now that is very powerful. So I think that embedding the knowledge that we do have from these 3D models of objects of the world within these generative models is definitely a compelling research and future direction. And with this, I conclude my talk and I'm open for discussion and question. Thank
Thank
you.
you, Alberta. So, lots of times for questions today. Todor.
Yes, I could go first. Thank you. Very interesting talk. I'm curious. Somebody might come, it wouldn't be me, but somebody might come and ask, why can't we just use one of these great foundation models to solve the cloth folding task? What would you tell them?
That's a very fair question, especially because if we go back to the very beginning, I think that especially now we do see some advances in foundation model to fold cloths.
Mhm.
Uh, my honest answer is that I think it's possible. I think like if you operationalize very well the data collection and you collect a huge amount of data, at least in a constrained environment, let's say in your specific house, I think that we are not that far to have a solution that uses this large foundation model. But the amount of data that you might need is challenging. So I'm not confident say that we can achieve that, but I do believe that if you do not mind about large data, and with large data I mean just for this
Mhm.
task, we are talking about 4,000 demonstration. So scale that for the number of objects that you're interested in. I think that that's possible. Um, I just don't think that it's easy to collect that amount of data. So to answer your question, why not? Uh, because it's not easy, and is it the question that we should be asking?
Mhm.
What's how much data should we need? I think that it's
I agree
likely
with
that
you. I agree with you. I mean, is it worthwhile doing,
exactly,
spending 4 years collecting data in order to train a foundation model? Or
exactly.
is it better to do something like what you're doing? I'm in the same camp with you. I think a model-based approach is more interesting to investigate simply.
I'm happy that people are also working on this foundation model
Mhm.
direction because I'm not the one that wants to collect data, but I do see a lot of benefits because then you can use these foundation models that still have some common knowledge because they were trained on so much data
Mhm.
that then you can come, or we hopefully can come with smart ways to generalize. You want a model or you want to introduce physics prior, then luckily someone will have collected enough data for us to make good use of that data. So I think it's a philosophy at some point. Which part do you want to take? And I appreciate more these structured approaches.
Thank you. I could ask a lot more, but maybe somebody else has questions as well.
Well, yeah, hang on to your questions, Todor, and let's see if someone wants to add one in between. I think they're all looking forward to your next one, Todor, so just fire
Excellent.
away.
So I had a PhD student who was working on deformable linear objects. So you're one dimension above him. But I guess there's a similar question for you. Most of these tasks to me look quasi-static. Is there something that actually requires a dynamics model? I mean, in the control sense of the word, not in the reinforcement learning sense of the word.
It's a very good observation. In fact, all my work uh, is done under the quasi-static assumption.
Mm.
I think that the need, specific need, not necessary, but there are some motions that might benefit from a dynamic model. Very common, for example, for cloths is using flinging action, so to flatten it. And that's a dynamic motion, which indeed involves dynamic control. Does it need a dynamic model? Well, probably you might want to predict the outcome. But for sure, there are some motions that require being dynamic. Or, for example, I can think of when you want to spread bed sheets. You can do it with quasi-static manipulation, but in the end, dynamic manipulation is more efficient. Allows you, for example, to reach better your space, because you don't need to reach all the points, but you can use the dynamic of your cloth to reach further point in the cloth. While with quasi-static, you really have the robot to reach some corners. So I think that dynamic manipulation extends the reachable space in the end.
Definitely. I'm just curious if your methods would scale to that, or do you see any kind of block for it at the moment?
There are a couple of bottlenecks in my method for now. I think that perception and representation are a big bottleneck for now, honestly, because I think that these bottlenecks are just due to engineering issues and maybe models that are very computationally heavy, but I would not be surprised if in a couple of years then these would be maybe not made real time, but that the perception part could be made faster. Also the model based, when you have a model, one thing that I haven't mentioned, but the model I used in my work are in the high-dimensional space of the robot. I actually predict and plan over the high-dimensional states of the full object, which is a bottleneck. For sure, latent space dynamics and parallelization could speed up the process, but the current state of my work right now has a bottleneck on the perception and on the planning part.
Is it some sort of MPC that you're using, or?
Correctly.
Yeah, okay. I think there's a question for you in the chat.
Yeah. Let me read.
Yes, and the question reads, how could you infuse physics priors into existing world models?
That's a very interesting question, and I like that a lot, because I think that there are a couple of ways that you can think of. So let's think about this dynamics model. So most of the way of learning dynamics model independently on the state space and the input space. Like for example, in this case, the input space is a mesh and it's an output another mesh. What happens instead for image-based model is that you give an input an image and you get an image as output. That's what these generative models do as input-output. One way that could be thought as introduced in priors, is creating, for example, a shared latent space. So if you enforce your model to get a shared latent space between images and meshes and 3D, then this latent space has this structure that you are searching for it or trying to enforce. So that's one way. The other ways, and this way acts on the representation space. The other way is instead acting on the model space. So you can have a data-driven model, but right now, current analytical model have become faster thanks to GPU acceleration, parallelizable, which when I started my PhD actually was not a reality. And the reason why I think like Gaussian splatting is really powerful is because then you can have your 3D state, your analytical dynamic model that takes care of all the physics, and then connect and bridge 3D with images with Gaussian splatting. So basically that's exactly what it does. It's like having a connection here, another arrow that points the 3D to the image. And at that point, you have a fully analytical and differentiable map. Assume that your analytical model being differentiable that connects images to 3D representation. So it's basically taking, you have image input, image output, but in between you have everything in 3D. You have 3D representation, your analytical model, output 3D representation, and then this bridge between images and 3D representation is made by Gaussian splatting, which I believe is a very challenging but interesting direction to explore.
Is there a follow-up question from the chat person? Thumbs up. Todor, you have
Yes,
one.
back to Todor.
Yes.
I'm asking out of curiosity because this, I think, is really interesting work that you have done. When you did the stretching, the elastic stretching, was that image space only, or were you feeling the forces on the end effectors?
So actually in this work, I simplified the visualization using images, but we actually used only force feedback.
All
And the
right.
reason is that the initial idea that was coming from Michael, that is here, was to learn elastic properties with a combination of images and forces. And it turned out that images were not that relevant, which I believe because forces is a direct way of measuring elastic properties, while if you don't have a pulling interaction, then probably observing the images and deformation becomes more relevant, while here forces were the strongest source of information that made images not relevant, even if we explored using images as well.
Okay, and in the later work there with Gaussian splatting, obviously you're working on image
Indeed.
space here.
Exactly.
So I'm curious what you think about the role of force sensing in these manipulations, because it's one of the often overlooked forms of perception, especially for all of these foundation models. They rarely take into account force interactions.
Yeah, that's very true. And I think that one of the reasons, so I will detour a little bit and then go back to the question of the forces. I think that one of the reasons why any other type of modality beyond vision is overlooked in foundation models is that the more modalities you insert in your training, the more data you need. So they can achieve like such a good success with images and text, but I would expect to be harder as soon as you start introducing more modality to achieve the same level of generalization and learning. So that's why I think that we do not see much of other modalities. And it's also impressive how much just vision can achieve, to be honest. It's great, but of course it cannot do everything. I think that without proprioception and without forces, then very fine and contact-rich manipulation is going to be hard, especially if you care about the forces. Because if you're in a peg insertion, if you don't really care how much force you're applying to the table or to the peg, probably vision is enough, because you just need to observe how far off you are. But that's not always the case. Sometimes, of course, you need some safety constraints if you have fragile objects or you want to observe tactile observations to make sure what's happening. But also, it's not just that, it's also the way I learned recently that humans learn to use tactile feedback before vision. So I think that is very much overlooked because vision can do a lot, but I'm pretty sure that is needed for some things. And right now we don't care too much about safety concerns, or we are not addressing tasks yet that require this level of precision. But I also think that is a very important modality that us humans use even more than what we realize.
Yeah, I think the first tactile neurons that develop are the ones that connect to the mouth. That's why babies put everything in their mouth in the beginning.
Exactly. Already when they're in the womb, they have no vision because they are in the dark. They see some light, but they have all the contact with the womb themselves. So yeah, the touch is developed before vision in humans. So that's an interesting thought and consideration.
But clearly, you're right. I mean, the problem is data availability, right? The internet is not full of force and tactile data, unlike image data or text data. So it's understandable why a lot of this work is done with vision in mind. But I think for many of these tasks, you need, or we're reaching the boundary what you can do just with vision alone. That's my feeling.
I agree.
Especially, yeah, something like what you're doing.
I think that also entails the type of problems the community addresses. There's a lot of pick and place, some insertion, some assembly. I mean, I don't want to be to provide an overview, but the main message is I think that we need also to bring the community to address tasks that require this type of sensing, because it's easy to assume that you don't need if you perform a pick and place task.
Cool. Thank you, Alberta. Very nice work and good luck with your PhD defense. I don't know when you're defending, but
Thank you, and thank you for the very nice questions.
I think Alberta is defending in January. Am I correct?
Correct, in 1 month, the
Yes.
14th.
So you can enjoy a longer version live if you travel to Stockholm.
yes. Well, it's not too far, maybe.
Okay, is there any final questions from the other audience? So let's thank the speaker again.
Thank you all
Well
for your
done.
time. It's been a pleasure.